Hey everybody, so in this video we are going to talk about antiderivatives. We're going to give the definition and we'll do some basic examples. Okay, so to start out, let's look at the definition. So the definition of an antiderivative so we have a function capital F is an antiderivative of f of x, right, or maybe just of f on an interval I if f prime of x is equal to f of x for all x in I. Okay, so we are using this capital F notation to denote the antiderivative. Okay, and so the idea here is that the antiderivative is the function whose derivative is what you're looking for, right? Okay. Right, so this is our antiderivative. Okay, so we're using big F for antiderivative and little f for the normal function, right? So we are looking, if we're looking for an antiderivative, then we are looking for a function whose derivative we are given. Okay, so let's look at some basic examples here. Okay, so we are going to find the antiderivative for the given function. Okay, so we have little f, right, which should be the derivative of our other function. Okay, now we know that to get x squared as the derivative, right, we know that our original function has to have x cubed, right, because we're using the power rule here, right? So think about what would happen if we took the derivative of x cubed, right? So if we take the derivative of x cubed, we know that we get 3x squared, right? Which is similar to what we want, but we don't want the 3, right? So we're going to put 1/3 here so that when we do take the derivative, this 3 and the 1/3 will cancel out, right? So we can check that it works by taking the derivative, right? Okay, so I have 1/3, and then the derivative of x cubed is 3x squared. Okay, so this is what I was talking about. The 1/3 and the 3 will cancel, and I'll just be left with 1x squared. Okay. Let's look at another example that we'll be able to just figure out what has that derivative. So something like x to the 5th. Oh. F of x equals x to the 5th. Okay, so again, we're going to be using the power rule, right? So we know that the antiderivative is going to have 6 as its power. Okay, and we're going to use this same idea, right? That when we take the derivative, that would give us 6x to the 5th. So we're going to use 1/6 to cancel that out. Okay, and again, we can always check that we have the antiderivative correct by taking its derivative. Right, so when we take the derivative, this will be 1/6 times 6x to the 5th, right? And these will cancel to give us x to the 5th. Okay, so we can see what's happening here, right? Okay. Now, one thing that comes up with antiderivatives, right, is are there other antiderivatives? We can check that these work, but are there any others? Okay. So let's think about this, and I want you to take time and pause the video and think about if there's any other function that would have that same derivative. Okay, so now that you've thought about that, let me show you an example of what I mean, right? So what if I picked the antiderivative f of x equals 1/3 x cubed plus 10, right? When I take the derivative of this, I have this same idea where 3 times 1/3 is 1, and I get 1x squared, and the derivative of 10 is 0, right? So this plus 10 doesn't change the derivative. So this right here is another antiderivative for x squared, right? We could pick another one. We could pick f of x equals 1/3 x cubed minus 2, right? This will still give us x squared here, and this minus 2 has a derivative of 0, right? So this will still have the intended derivative x squared, right? So changing these constants doesn't change the derivative, okay? Now, this is supported by that corollary to the mean value theorem. Okay, so let's talk about that really quick, and then we will talk about, in general, what we do with this information. Okay, so remember from when we talked about this corollary, right? Okay. Okay, so if f prime of x equals g prime of x on an interval, right? Then f of x equals g of x plus some constant on that interval. Right? And this supports our idea that the antiderivative is going to have a main part, and then it can have a constant because that really doesn't affect the derivative. Okay? So let's look at a theorem that states exactly what we just talked about, right? That the constant doesn't affect the derivative. So there's a whole bunch of antiderivatives that have the same main features and then a constant. Okay. So this explains exactly what we just said. If you have any antiderivative on that interval, then the most general antiderivative is that derivative plus some constant c, okay? So let's look at an example of finding all of the antiderivatives, right? And we represent them with this most general language plus c. Okay, so we're going to look at some of the basic types of functions that we know the derivatives of, right? So we're going to look at power functions like x to the n, right? But we're going to specify for n is not -1, right? So this isn't 1 over x, okay? Anything besides 1 over x. And then separately, let's talk about what the answer is for 1 over x. Okay. All right. So this is what we were looking at in the first example, right? Where we had x squared and x to the fifth, right? So when we look for the antiderivative, we know that the exponent is going to be 1 greater, right? Kind of the opposite of the power rule where you take 1 away from the exponent. Okay? And then if we don't want any coefficient here, we'll have to cancel the coefficient out by putting 1 over n plus 1. Okay? Now, what do we mean by the most general antiderivative, right? So this is when we need to add plus c to show that the antiderivative could have any constant part to it, and it wouldn't still give you the exact same derivative, x to the n. Okay. Now, again, this doesn't work for 1 over x. So what does work for 1 over x, right? So in this case, we really need to remember what function has the derivative 1 over x. Okay. If you take the derivative of natural log x, the answer is 1 over x. Okay, so with that information in mind, we know that our antiderivative for 1 over x is going to be natural log x. Okay, and then again, it could have any constant, so we put plus c. Okay, so any power function that is not 1 over x, and then 1 over x. Okay, let's look at a couple more that we know where they come from. Okay, so we're looking at the trig functions here. So we know that cosine is the derivative of sine, right? So the antiderivative is going to be sine x, right? And then the most general antiderivative says, and any constant. Okay, they will all have the same derivative, right? So the derivative of sine is cosine, the derivative of the constant is 0. Okay. Now it's really similar here, right? We know that the derivative of cosine is negative sine, right? So if we were just to put cosine x, this wouldn't be quite right because that would give us negative sine x. So we're going to put a negative so that when we take the derivative, we'll have negative sine x. Okay, so let's check and make sure this works. Right, so I have the minus sign from here, okay, and then the derivative of cosine is negative sine. Okay, so you can see that the minus minus is going to give us positive sine x. Okay, so this does work. And we still need to include our plus c to say that our antiderivative could have any constant you want. Okay, so here are some basic types of functions, right? We have power functions, we have 1 over x, and we have 2 of the basic trig functions. Let's look at some other types of functions that we have talked about their derivatives, and we will talk about their antiderivatives. Okay, so remember e to the x is its own derivative. Okay, so that means when we're looking for the antiderivative, we want it to be e to the x, right? You take the derivative of this, you end up with that. Okay, and then we need to include our constant, right? That doesn't affect the derivative. Now for b to the x, right, for a different base, it's important to remember the derivative, right? So remember when you take the derivative of b to the x, what you get is b to the x natural log b. Okay, so when we do the antiderivative, okay, we do want b to the x, okay, but we want to cancel out this natural log b, so we put 1 over natural log b. Okay, and then we still include our constant, right, because that doesn't affect the derivative. All right. So the last couple of functions here okay? Now for both of these, we really just need to recognize these as the derivative of a function that we know. Okay, so remember, when you look at the derivative of sine inverse, okay, the derivative of sine inverse is 1 over square root of 1 minus x squared. Okay, so we recognize this as the derivative of sine inverse. So its antiderivative is sine inverse. Okay, and then we have our plus c because we know that our constant doesn't affect the derivative. Okay, now similarly here, we need to recognize 1 over 1 plus x squared as the derivative of something. Okay, there's no way to just magically figure it out, but we need to remember that the derivative of inverse tangent is 1 over 1 plus x squared. Okay, so if we're feeling like, oh, I really didn't remember that, it would be good to review the derivatives of the inverse trig functions. Okay, so this is going to be tangent inverse or arctangent, right, plus any constant c. Okay, So this is how to find the most general antiderivative. Okay, that plus c makes it the most general. Okay, and mostly we are thinking about what functions we know gives this as a derivative. Okay, all right. Those are the examples that I wanted to cover for this video. So in the next video, we will look at a couple of more complicated examples. So I will see you guys there.